Hi, my name is Samuel Figueroa. This summer I worked in the Department of Material Science and Engineering under Dr. Christopher Hsu, and today I will be giving a review of a specific field in metallurgy that my project is based on regarding a novel sintering technique for producing nanocrystalline alloys using phase separation. Before we get into more details, I think it is best if we start with a few basic definitions. Crystals are the fundamental units for all solid materials and are repeating ordered lattice structures of atoms that can be modeled using vectors in a 3D space. Common metal crystal structures are typically cubic or hexagonal structures of atoms. If we zoom out of the atomic scale onto the surface of a metal, we can see that the metal is broken up into units called grains and divided up into grain boundaries, areas of high concentrations of instability due to lattice distortion. Based on various mechanical principles, such as the Hall-Petch effect and the movement of atomic defects in a material, it is known that nanocrystalline grains of roughly 300 nanometers or less have shown remarkable strength, hardness, stiffness, and other properties, and are a hot topic in metallurgy due to the difficulty in making them. A novel technique called nanophase separation sintering has recently emerged as a promising candidate for the production of bulk nanocrystalline alloys. We start with a solid solution of metallic solvent particles of micron size with nanocrystallinity and saturated with a secondary element. Upon heating, the solvent and solute phases separate from each other, and the solute migrates to the outskirts of the solvent particles to form necks between other solvent particles. As heating continues, sintering is triggered as atoms of both the solvent and solute rearrange themselves and quickly move across the neck bridge as the material rapidly densifies, until the material fully sinters at a significantly lower temperature than conventional sintering methods. The criteria for NPSS is quite simple and intuitive, and can be elucidated using a phase diagram or a graphical representation of phase changes over heating. After the onset of heating, the first criteria that must be met for a binary alloy system is phase separation, which one can reference using a phase diagram like the one shown. Secondly, the melting temperature of the solute element must be lower than that of the solvent element. This is tied to the fact that this process requires the solute element atoms to have lower surface energy than the solvent in order to migrate to the grain boundaries and move to create necks between particles, where surface energy is directly proportional to melting temperature and can also be referenced on a phase diagram. Finally, the solvent must be able to dissolve within the solute in order for the solvent atoms to travel back across the solute neck bridges to fully sinter the bulk material. The methods for preparing metallic powder particles for MPSS is very straightforward, and this is one specific example taken from a recent paper. First, taking powders of both a solvent and a solute, the powders must be ball milled, a process by which tungsten carbide balls impact the powder particles to input mechanical energy and further distort crystal lattices and thus create more grain boundaries. This is so the solute atoms do not have to travel farther distances to reach grain boundaries if the grains are smaller. The powder is then compacted by die cold pressing uniaxially using a pump and then put into a thermal mechanical analyzer for sintering. After the material is fully sintered and densified, the material grains and microstructures can be characterized using electron microscopy and X-ray diffraction. The results from a few recent papers using NPSS has shown that in tungsten chromium and chromium nickel alloys, nanocrystallinity in grain microstructure is achieved in bulk sintered parts, as shown in the electron microscopy images. Through further inspection, it can be shown in situ that the stages of NPSS are occurring through the imaging of the necks between solvent particles. This is very promising as a novel method for fabricating both nanocrystalline structures and bulk materials with nanocrystallinity, owing to the unique rapid diffusion transport of atoms across the necks formed through NPSS that can prevent grains from coarsening. Potential future work within this area is exciting for the field of metallurgy and its wide range of applications. For example, NPSS could perhaps open doors for use in the production of geometrically complex parts. NPSS could be expanded to other binary alloy elements and perhaps even to other kinds of materials outside of metals. Finally, the mechanical and thermal performances of these alloys using NPSS is yet to be fully explored and can yield interesting applications in materials for aircraft and spacecraft, vehicle armor, and low-cost structural materials. And I hope to follow this research as it grows. I would like to acknowledge the MIT Office of Graduate Education and MSRP for this opportunity, specifically Dr. Wakefield and Maria, as well as my faculty mentor, Dr. Hsu, for his expertise and generosity, as well as the rest of the SHU group, including Christian and Yannick, for their unwavering support. Thank you for listening.